We have talked about static equilibrium before, but we're going to discuss one more condition because now we have more knowledge about torque, and so torque is going to add a condition to static equilibrium. So, and this is in particular important when, for civil engineers, right? You want to, when you build structures, you want to keep objects static, right? So you need to make sure the net force on the system is 0, and then you also want to make sure that the net torque on the system is 0. So in other words, the object is in complete static equilibrium. So this is just an example of, you might have seen this. I've seen one of these rocks in the Garden of Gods in Colorado. So it's a good example of how an object can be in static equilibrium. So the conditions that we're going to look at now, so we saw these conditions, that the net force on an object is 0, then object, so we talked about, if you go back to the lectures, we talked about dynamic and static equilibrium, right? Dynamic equilibrium is net force equals 0 means that the acceleration is 0, and then that means that the velocity is constant. So when that constant is 0, then we have static equilibrium. And so is the case for torque. If the angular velocity is 0, and so angular velocity is 0, and then a linear velocity is 0, both of these two conditions are what we're going to assume to be true for an object to be in complete static equilibrium. So let's look at this question, and what do you think, which of these objects is in static equilibrium? So which of these objects, in other words, have net torque equals 0 and net force equal to 0? We're going to assume that the object can rotate around its center. Okay, so what do you think? Pause the video and think about the question, and we'll discuss the answer. Okay, so the answer is D. Now you can see that, so let's go through all of these. You can see that for this object, right, you can see that there is, if you look at, you look at the forces, you add these two forces together, there's a bigger force to the right than to the left. So this object is going to undergo linear motion also, right? And then you can see that the torque due to these two forces is 0. So there's a net torque acting on it, right? So it's neither in a linear translational equilibrium, and also not in rotational equilibrium. So the net torque is not equal to 0, and then the net force is not equal to 0 also in this case. And so in this case, you can see that there's again a big force like to the right. These two add up to give you a bigger arrow, right, to the right than to the left. So this is going to undergo linear motion, but you can see that the torque, right, is the net torque on this is 0, because the net torque on this force due to this force is 0. It goes through the center or the pivot point. This produces clockwise torque. This produces counterclockwise torque around this pivot point. So the torques due to these two is cancelling out. So net torque is 0, but the net force is not equal to 0. So it's in rotational equilibrium, but it's not in translational equilibrium. This system is in translational equilibrium. The net force on this side, the total force on the right is equal to the total force on the left. But you can see that there's a big torque acting on this system. So these two add up to give you like a force that is, in this direction, right? So this this produces clockwise torque, and this also produces clockwise torque. So this is a big torque. There's a big torque acting on this. And so the last one is the answer. There's you can see that the forces on the right add up to balance the forces to the left. So there is no linear motion. The net force is 0, and then the net torque is also 0. The torque due to this force is 0 because it goes through the pivot point. The torque due to this is clockwise. This is clockwise. This is counterclockwise. So they cancel each other. So this is why this is the answer. So when we solve problems related to static equilibrium, there is an important point to consider, and that's regarding the pivot point. So the pivot point can be any point especially when it's in static equilibrium. You don't know where the object is going to rotate around. You don't know the point. You can choose anything as the pivot point. And a smart choice is always to choose a point so that one of the forces is at that point. So that means that your calculations are going to be easier, because any force that goes through the pivot point, the torque due to that force is going to be 0. So that makes the calculation easier the calculations easier to solve when you're applying the condition of static equilibrium. Okay, let's answer this question. What do you think is the scale gonna read, right? This is a massless rod, and there is a weight hanging over here, right? And then there's a scale over here. What do you think is going to be the reading on this weighing scale? And yeah, so think about the conditions of static equilibrium. Pause the video. Okay, so the answer is 2000. Right, so you can see that the weight is over here, right? This is the weight. The rod is massless, does not have a weight. There's a normal force acting on this. So you can conceptually think about this also. So this distance is L by 2, right? This is half the length, right? So when you there is 1,000 Newton force acting at a distance L. So if you decrease the distance by L by 2, this reading has to increase by 2, right? So it makes more sense if you do the calculation, right? So when you apply the condition that the net torque is 0, right? So net torque is equal to 0, means that this weight, right, its torque is W times L, right? And you can see that it's clockwise, right? And this is counterclockwise, so they balance each other. This is the pivot point. We're assuming there are obviously forces over here. We don't have to consider those because this is our pivot point. So this normal force, right, has a distance L by 2. So weight times L is equal to N times L by 2. So again, torque is R perpendicular times F, right? So we're just multiplying the distance with the force. So distance times force is W times L over here, and then distance times force is N times L by 2. And the torque due to these two forces balance each other, and when you set them equal to each other, the L cancels out and you get normal force equals twice the weight, and so the reading is 2000 newtons. Okay, so let's look at this question. In this question you have a uniform plank and leans against a frictionless wall. You have to figure out the torque at around point P applied to the plank by the wall. So the wall applies a torque on the plank. So obviously the wall has normal force, right? There's a normal force acting from the wall, and so let me get my arrows. Oh, okay, it's not working. Anyways, so I'll just draw it in my head. Okay, so the normal force is that, and then there is a weight, right, which is given, right? So the weight is 80 newtons, right? That's the weight of the plank. Now we need to figure out the torque due to the normal force, and that's N times. So N times you extend the line of action of the force, this distance, that's 4 meters, right? So that's N times 4 meters, right? So we don't know what the normal force is, right? We need to figure it out, and so we can apply the condition of equilibrium. That the net torque on this system is 0, so N times 4. Okay, so this is counterclockwise. Let's emphasize on so the net torque is equal to 0. I'm just writing the total torque. So N times 4 meters minus W. So if you extend the line of action of W, so this distance is half of 3, right? So 3 by 2 meters, right? And so that should be equal to 0. The net torque on the system should be 0. So this is again normal force times 4 meters. The normal force, the perpendicular distance is 4 meters. It's counterclockwise torque, and this is clockwise torque around the pivot point, and this distance is 3 by 2 meters, right? So so when you solve this, you get N equals 3 by 8 times W, and so W is given as 80 newtons. So this gives you 30 newtons. So that's the normal force. That's obviously not, we're not looking for this. We're looking for the torque. So torque is 30 newton times 4 meters, right? So that's 120 Newton meter. Okay, so that's the answer. The answer is C. Okay, 120 meters. Okay, so let's look at this problem. So in this case, you have a weightless, again weightless, in this case a weightless strut, and then the length of the strut is 5 meters, and then it's used to support an 80 Newton, so that's the weight of the block that is hanging over here. So you have to find the horizontal and vertical components of the force of the hinge. So there's a force acting from the hinge. It has a horizontal component, Fx, and then a vertical component, Fy. So so then there is obviously a force of tension, right, that is on the string over here. So that's T1, the cable tension, right, and then this is T2. And so, well, yeah, let's call this FH. So let's use those symbols, right? So FH and then FY. Let's keep the symbols the same. It doesn't matter. So so now we know that the system is in equilibrium, right? There's no there's no weight of the rod, so you don't have to worry about that. So these are the forces that are acting on the strut. So the strut is our system, so we need to focus on what the forces are acting on the forces acting on the strut. And so this tension, you can see, is going to be equal to the weight. It goes up over here, and then weight is down over here. So so tension T1 is equal to the weight. So if you apply the net force equal to 0, you can see that if you focus on the strut, the vertical force, this vertical force is equal to the to tension, right? So Fy is equal to T1, and then T1 is equal to weight, and so that's 800 newtons. So the answer is going to be either this one or this one. Okay. Oh, sorry, no, my bad. Okay, so it's either going to be this one, because Fy, we're looking at Fy. So let me erase that. Okay. So there you go. It's either going to be this one or this one or this one. So, well, 4 possibilities, right? Because we found Fy, and that's 800 newtons. So now let's look at the horizontal component, right? So this is our FH, right? This is FH. So FH is equal to T2. So if you look at the system, FH is equal to T2. So now, how do we get T2? So this is where it gets a bit tricky. So we need to find we need to apply the condition of equilibrium that the net torque on the system is equal to 0, right? So let's apply the condition of equilibrium, the net torque equal to 0. So so let's do that where net torque equals 0. So the torque due to, so we're going to choose this as the pivot point. Again, the pivot point is always yours, you know, it's always a smart choice. We're going to choose this pivot point so that we can find T2. We don't have to worry about these two forces then. So you can see that the torque due to T2 is counterclockwise, and the torque due to T1 is clockwise. So and the distance of T1, the line of action of T1, right? The distance is 3 meters. So this is the line of action of T1, and this distance is 3 meters, right? And the line of action of T2 is this one, right? And then this distance, you can use the Pythagoras theorem to see that this is 4 meters. Right? 4 squared plus 3 squared is should be equal to 25, and then square root of that is 5, right? So you can use the Pythagoras theorem to get that. So again, you apply the condition of equilibrium, T1, negative T1 times 3 meters, and plus T2 times 4 meters, equal to 0. So again, T1, this is the line of action, right? And then the distance is 3 meters, and then this is the line of action of T2, and the distance is 4 meters. And so when you do that, you get T2 equals T1. You simplify the equation, you get T2 equals T1 times 3 by 4, and that's 600 newtons. Because we know T1 is 800 newtons, you plug that in, you get 600 newtons. And so therefore, this is the only one with 600 newtons. Is the answer. So that reduces the possibilities and gets rid of every other choice we thought might be the answer. Okay, so the answer is B. Okay.